Okay, grade 8s, we're going to look at 8.5, constructing tessellations. So in 8.4, we look at the different types of transformations that can, how you can kind of manipulate a shape, either rotating or reflecting or translating. And so we're going to see where we recognize some of those transformations in what's called a tessellation. So anytime you can use a shape to cover a plane, so basically just covering a space, a 2D plane, where there's no overlaps or gaps. That's the key to what a tessellation is. Then we say that it tessellates. So a typical example, even another name for it, is called tiling the plane. If you've ever tiled your bathroom or your floor or something like that, you'll notice you run into problems if you aren't, if you're having gaps or if you're overlapping, it's not going to work. Right, so if a shape does that, we call it a tessellation. Okay, so not all polygons tessellate, some of them do. This example was used in 8.4, kind of these L shapes. This one does tessellate because we can put another shape, an identical shape down every time, and just by rotating it, we plug them together, kind of like a puzzle. And if it works, it works. Now, one thing that you'll notice is the angles, and we'll touch more on that in a bit. But the angles inside of a tessellation in the middle will always equal 90 degrees, or 90, 90, 90, 90, so it'll always equal 360 degrees. Okay, so if that's the case, if the angles add up to 360 in the middle, then you'll be able to tessellate a shape. Okay, so a couple examples here. This is a hexagon that does not tessellate. We see that there's a gap. However, we're also going to look at a little bit later, I think in 8.6, compound tessellations, where this actually does tessellate if you consider that the square works to fill the gap. And so if I include the square and I had another tile that was a square, then I'd say, yeah, this tessellation does work. Okay? We'll just keep rolling through a few examples here that are in your book that you can take a look at. Here's a triangle. You can see that if you added up these angles, it's going to add up to 360 degrees. It works out. Same with these triangles, different shaped triangles, but if we add up the different angles, you'll see that it fills the 360 degrees. Okay, different four-sided shapes, doesn't really matter. They could be wonky shapes. I could kind of put them together. As long as this adds up to 360, it's going to work. And I could kind of think of it now as one shape. If I took another one of those exact same shapes, I could use that. It'd be kind of a wonky one, but it would work. Okay, same thing here. If I add all these up, it adds up to 360 degrees. So that's the whole key to whether or not you have a tessellation that's going to work. It can't have overlaps and gaps, so all the angles need to add up to 360 degrees. Okay, so we'll look at a couple of examples here. Does each shape tessellate? So we'll just take a look. You will probably find here, if I draw this one out, you could maybe get it to tessellate once or twice, but not all of these are going to continue, right? So for example, I could, right here, I could put them side by side with one another, and I'd be okay. I could kind of keep going, but you might even be able to do this one, right? One even further, like that. But you're gonna at some point run stuck because of the triangles. So does this shape tessellate? Yeah, I could tessellate once, right? You could say this is 360 degrees, but where would I go from here? You're gonna run into trouble. So this one doesn't tessellate. Okay, so some of these you might just have to play around with a little bit. This one, if I drew this, you could, I believe, make it tessellate. So if I just started doing one of these every time, you might think, oh, you might run stuck if I put it on top, but if you were creative with it and you staggered it a little bit, you could see that that's going to fill the gap every time. So B does indeed tessellate. This one won't work for a long period of time. This one will. Okay, this shape here, four-sided shape, again, you can play around with it and kind of see if it's going to work. If I just kind of flip that one around and did one of these, then you can see that it is going to tessellate every time. If I just kind of kept that pattern going. So this one can as well. So sometimes you can see them pretty quick. Sometimes it might take a little bit to actually recognize whether you're tessellating. Notice in these tessellations, you're using some transformations. These are being slid over, or you could say they're being reflected. This one's kind of being rotated and then slid over. You see that you're using those transformations in order to make a tessellation. Okay? Same example too. Look at each shape that does not tessellate. There was just one that didn't tessellate. Try to combine it with the other shape. So maybe some of you are already seeing that this is the one that didn't. Could we combine this? Well, if I notice this part of the shape and this part of the shape, maybe you can start to see where those two shapes could fit together. And that's often what ends up happening with some of these complex tessellations, is they're actually a simple shape that's kind of been split up or changed or added to another shape in order to make it tessellate. So this one didn't tessellate when I was doing this, but if I now take the second shape and add it to my spot, then you might notice, okay, this actually does work if I just kind of put that together. So this is what we call a composite tessellation, or you could imagine that these are all kind of forming that T shape, which is going to work, right? I just think of that as just one shape, and this is another shape, and this is my upside down T shape, then it works like that. Okay, and you could keep that pattern going for a while. Okay, but it's enough to show that this is going to keep going if I keep tessellating it. Okay, so that's pretty much all there is to it. You're going to take a look at some of these tessellations. Now, one other thing, so we call that a composite shape. One other thing that I will look at is just whether or not certain shapes will tessellate. And so this is going to be one slide that you'll want to take a look at. There's a few questions that I ask you on a worksheet or on a quiz, just identifying whether or not a shape is going to tessellate. And you can actually tell just by looking at how many sides. We looked at a triangle already previously and a four-sided shape, and it's actually going to work out that any three-sided shape or any four-sided shape will always tessellate. This you can use, it can come in handy. I'll just go through it in one of the examples here. And then other than that, if you can remember this, then you can just use this. So I'll just touch on this whole thing for a minute. So the sum of the angles in any shape is equal to, here's a formula we actually use more in grade 11 in the Dash 2 stream, but for us, we don't really come across it. We use it just a little bit here. But anyways, the sum of the angles in the shape is equal to 180 times the n minus 2, where n is the number of sides in the shape. Okay, so I'll just take you through this with, let's say, this example with an 8-sided shape, and it'll probably easier if you just see this formula being used. Okay, so we plug this in. If I want to know the sum of all the angles in an 8-sided shape, okay, so here's my 8-sided shape, or in other words, an octagon. If I want to know the sum of all the angles in here, I take 180, the sum is equal to 180 times the number of sides, which is 8, so 8 minus 2. Okay, 180 times 6, in other words. Okay, when I do that, you end up with a certain number, 180 times 6. Okay, it is written there, so it's equal to 1080. So that means, no matter what, this is like a regular octagon, which means all the sides are going to be the same, which means the angles would be the same. So in a regular shape, all the angles would add up to 1080, and they'd all be the same. So we could actually figure out each angle in the regular shape by taking this and dividing it by 8 sides. So if I divide it by 8, we do indeed get the 135 that it says. So that's what this part of the formula is telling us. We're basically just taking that top part and then dividing it by how many sides you have. Okay, so that's all we're doing here. Divide by 8 is 135 degrees. Now, for tessellations, we know that 360 degrees, right? That little rule, if the angles make up 360 degrees, then the angle's going to work. So we can do a quick check just by doing 360 degrees divided by 135. If this number comes out to be a whole number, which it won't, in this case it's 2.6 repeat or 2.67, then no, it's not going to overlap. What that essentially means is when you start to try to overlap this thing, you could draw another octagon here, but here you can notice there's not enough for another full octagon. So no, the shape does not tessellate on its own. So all these ones that have a no, I've done the math for you. You can just basically, what you need to do is know that any 3-sided shape, it's going to work. Any 4-sided shape, it's going to work. any six-sided shape could work. So 3, 4, and 6, as long as they're not too wonky. Okay, so if they're just kind of the regular, typical type shapes. Okay, so those ones are. So this one does tessellate, so does this one, so does this one. Otherwise, you can go to this formula and use it to figure out the angles in a shape. Okay, so that's a little something you'll need. I think for number 7 on here, page 467, you have a few questions to practice. Number 7 gets you to action, 7 and 8 get you to look at that. So use that little formula, use the little table that I give you.